Hello everyone, section 2.3, postulates and diagrams. Example 1, state the postulate illustrated by the diagram. So we have if a line, then these 2 points A and B are on that line. Well, that's the line point postulate. Okay, in the second one here, part B, if we have these 3 points, and what do we notice about these points? These points are not lining up, making them non-collinear. So if 3 non-collinear points, so if we have 3 non-collinear points, then in this next picture we have these 3 non-collinear points in a plane. Well, that's the 3-point postulate. Okay. Example 2 is a whole bunch of always, sometimes, and never questions, and these can be tricky. You would think something where it's just a choice of 3 simple answers would be simple, but they're really not. Sometimes they can be very tricky. So let's take a look. Intersecting lines are always, sometimes, or never coplanar. So this is a fairly simple, straightforward one. Intersecting lines are always coplanar. 2 planes always, sometimes, or never intersect in one point. 2 planes never intersect in one point. 3 points are always, sometimes, or never coplanar. 3 points are always coplanar. Even if they're collinear, they're going to be coplanar. They're going to be an infinite number of planes, but they're still coplanar. Part D, a plane containing 2 points of a line always, sometimes, or never contains the entire line. This would be always. And we're going to see this question again in example number 10. And we're going to talk about why this is true. Part E, 4 points are always, sometimes, or never coplanar. This is a sometimes. If you've ever sat in a chair that rocked back and forth, it's got 4 legs and it rocks back and forth, it's because one of the legs is not in the plane of the floor. 3 points have to be coplanar, 4 points do not. F, 2 lines always, sometimes, or never meet in more than one point. 2 lines never meet in more than one point. 2 points always, sometimes, or never lie in exactly one line. 2 points always, sometimes, or never lie in exactly one line. 2 points always lie in one line. 2 points are always collinear. 3 points always, sometimes, or never lie in exactly one line. Well, this is very similar to the 4 points are coplanar. 3 points are sometimes collinear, and sometimes they're not. To answer these questions, it's oftentimes good to say, can I draw a situation where this is true? Can I draw a situation where this is not true? If I can draw a situation where this is true, and I can draw a situation where this is not true, then the answer is sometimes. If I can only draw a situation where it's true, then it's always. And if I can only draw a situation where it's not true, then it's never. So 3 points always, sometimes, or never lie in exactly one point, in one plane. This one is tricky because this is sometimes. This is different from 3 points are coplanar. 3 points are coplanar is true. They're always contained in the same planes. Now there may be more than one plane that contains them in the case if they're collinear, but this is true. This is always true. 3 points sometimes lie in exactly one plane because sometimes they lie in more than one plane. That's why I is sometimes and C is always. J. 3 collinear points always, sometimes, or never lie in exactly one plane. 3 collinear points always, sometimes, or never lie in exactly one plane. This is never because 3 collinear points always lie in an infinite number of planes. Okay. K. 2 planes always, sometimes, or never intersect. This one is sometimes. Sometimes they intersect and the intersection is a line. Sometimes they never intersect and the planes would be parallel. An example would be the ceiling and the floor, or the front and the back walls, or the left and the right walls. L. 2 intersecting planes always, sometimes, or never intersect at one point. They never intersect at one point. 2 intersecting planes always intersect at a line. M. 2 intersecting lines always, sometimes, or never intersect in exactly one point. This is always. 2 intersecting lines always intersect in exactly one point. 2 lines always, sometimes, or never intersect in exactly one point. Now this is a little bit different. M and N are not saying the same thing. Why? Well, in M it says 2 intersecting lines. In N it just says 2 lines. 2 lines might intersect in one point. They might never intersect. They could be parallel or skew. So this is a sometimes. So this is a good example of I can draw where they intersect at one point, and I can draw where they never intersect, making it a sometimes. O. 2 intersecting lines always, sometimes, or never lie in exactly one plane. This is the same as question A. Intersecting lines are coplanar. 2 intersecting lines always lie in one plane. P. A line and a point not on that line always, sometimes, or never lie in more than one plane. The answer is never lie in more than one plane. A line and a point not on that line are always coplanar, and this is again something that will be explored in example 10. Part Q. A line always, sometimes, or never contains exactly one point. This is never. A line contains an infinite number of points. When, part R, when points A and B are in a plane, line AB is always, sometimes, and never in that plane. This is an always, and again, will be explored in example 10. All right, example 3. Use the diagram to write an example of the 3-point postulate. So we have to find 3 points that are non-collinear, that are basically defining one of these planes that is shown here. So we have plane Q and we have plane P that are being shown here. So if I take a look, plane Q doesn't have any points drawn in it. Plane P has points A, B, and C. Now notice A and B are collinear, A and C are collinear, B and C are collinear, but A, B, and C are 3 non-collinear points. So points A, B, and C are three non-collinear so there is exactly one plane, in this case plane P, one plane, plane P, that contains them. Okay, example 4. State how many segments can be drawn between the points in each figure. No 3 points are collinear. So if we have 3 points, how many segments can connect them? 3 segments. Part B, if we have 4 points, how many segments can we connect them? 1, 2, 3, 4, 5, 6 segments connect them. If we have 5 points, 1, 2, 3, 4, 5, how many segments connect them? I'm not going to count them all right now. There are 10. You can count them. If there are 6 points, 1, 2, 3, 4, 5, 6, making a hexagon, then again, I'm not going to count all the segments, but you can count them. There are 15 segments here. Okay, so that was part D. Part E, without making a drawing, predict how many segments can be drawn between 7 points and no 3 of which are collinear. So if we had 3 points gave us 3 segments, 4 points gave us 6 segments, 5 points gave us 10 segments, 6 points gave us 15 segments, 7 points are going to give us how many segments? So we go look for the pattern. Okay, use our inductive reasoning from the last section and see if we can figure this out. Going from 3 to 6, we've increased by 3. Going from 6 to 10, we've increased by 4. Going from 10 to 15, we've increased by 5. I'm seeing a pattern. I'm now going to increase by 6. So 15 plus 6 is 21 segments. That's our answer to part E. Part F, how many segments can be drawn between endpoints, no 3 of which are collinear? So now we're going to take this to the next level and we're going to come up with an expression that will find the number of segments given any number of points. Okay, so again, using your inductive reasoning skills that you gained in the last section, we now need to make a connection between the 3 and the 3. And the same connection has to work between the 4 and the 6. So it can't be just n is equal to number of points and it's equal to a number of segments, because yes, that works here for 3 and 3, but it doesn't work here for 4 and 6. N is 4. The number of segments is not 4. The number of segments is 6. So we need to find a different relationship. So what can I do to 3 to get 3? And it's going to be the same thing that I can do to 4 to get 6. And it's just the same thing I can do to 5 to get 10, 6 to get 15, 7 to get 21. Okay, so what is that we can do? Well, this one's harder to see because this is just, it looks like a direct relationship. So we'll have to do something else. Let's take a look at this one. 4. 4 times something. Now, 6 is half of 12. 12 is 4 times 3. So 4 times 3 divided by 2 is equal to 6. 3 times 2 is 6 divided by 2 is 3. 5 times 4 is 20 divided by 2 is 10. 6 times 5 is 30, divided by 2 is 15. 7 times 6 is 42, divided by 2 is 21. N times n minus 1 divided by 2 is the answer to part F. Okay. Example 5. Rewrite the following statement as two statements. So we're going to rewrite the following statement as two statements, one describing existence and the others describing uniqueness. What existence and uniqueness statements is described in the previous page. So you can read through that so that you know what that means. The original statement, an angle has exactly one bisector. To rewrite this as a statement of existence, we want to say that we have an angle, and every angle that we have has a bisector. So every angle has a bisector, at least one bisector. So what this is saying, that there's at least one bisector. There could be more, but there is at least one. That's a statement of existence. Another statement of uniqueness would be an angle has no more than one bisector. This is a statement of uniqueness, meaning there is exactly, this is also a statement of uniqueness, but I'm rewriting it to say that it has no more than one bisector. So it has exactly one bisector. That is a statement of uniqueness. Example 6, sketch diagram showing ray Vx intersecting line UW at point V, so that Vx is perpendicular to UW, line UW, and points U, V, and W are collinear. So I'm going to actually start with the line UW, W, and then I'm going to point V in between U and W, and then draw ray Vx, and put X up there, and indicate that it's perpendicular to the line. So there's a sketch of the diagram showing all that information. Example 7. Draw a figure for the line intersection postulate and state in terms of the figure what is given and what is to be proved. We're not going to actually do the proof. So the line intersection postulate is if two lines intersect, then the intersection is a point. I'm paraphrasing. So I'm going to draw two lines. And I'm going to name one of them M and the other one N. They're intersecting at point C. And what information would be given? Well, we're given when we're trying to prove a theorem, we can't prove postulates. Postulates are accepted statements of fact. They're too basic. We can't prove them. But theorems, which are written in the same if-then form as postulates, conditional statements, when we go to prove theorems, the given information is the part following the if, and what we're trying to prove is the part following the then. So the given is the hypothesis and the conclusion is what we're trying to prove. So in this case, we're given lines M and N intersect. We want to prove that M and N intersect in exactly one point C. Okay. Example 8. Which statements cannot be assumed from the diagram? So we have this diagram up above here. There exists a plane that contains points A, D, and E. Well, A, D, and E are three non-collinear points. So even though it's not drawn in the diagram, there is a plane that contains points A, D, and E. It has to be, because they're three non-collinear points. And the three-point postulate guarantees that they have to be contained in the plane. All right. The measure of segment AB is equal to the measure of segment BF. So the measure of segment AB is equal to the measure of segment BF. So even though they appear to be equal, we cannot make that assumption. We can't look at that and just draw the conclusion that they are equal. So this is the one that cannot be assumed. Okay. Example 9. Sketch and label the figures described. Use dashes for parts hidden from the view. So vertical line L intersecting horizontal plane M at point O. So I'm going to draw plane M. There's plane M. I'm going to draw a vertical line L. Notice the dotted parts or dashed parts for when it goes through the plane and it's hidden by the plane. Then it comes out. Now again, planes go on forever and ever. This is just a representation of the plane. It's intersecting that plane at point O. So, and this is line L. Okay, so that's the drawing for part A. We're going to draw horizontal plane P, contains lines K and N that intersect at point A. So I draw a horizontal plane. I'm going to try to. I can do a better job than that. That didn't come out very good. That's only slightly better. So here I have my horizontal plane P. In it we're going to draw line K and line N. Lowercase. And they are intersecting at point A. Okay. Part C, horizontal plane Q, vertical plane N, and they intersect. Well, they would have to. If one's horizontal and the other one's vertical, and they go on forever and ever, at some point they're going to intersect. So this is a little tricky with the dotteds. So I'm going to start off. Let's start off with the vertical. Actually, it doesn't matter which one I start off with. They're both kind of tricky to draw. And notice I stopped about halfway, maybe even a third the way, because now I'm going to start drawing the horizontal one and showing the dotted for where it goes behind the vertical and it comes back out. Horizontal front goes perfect all the way through, no dotted. Same with the front of the vertical, no dotted. But now part of the vertical back has dotted. And it comes out. Finish off the bottom. And what I haven't drawn is the intersection yet. So they intersect here at this line. I can even draw that line continuing, because in reality these two planes, N and Q, go on forever and ever, making the intersectional line which goes on forever and ever. Okay, part D. Vertical planes X and Y that intersect at line AB. So a little tricky here. I'm going to start top by drawing an X. I'll make this the tails of the X down here a little bit longer than the top. And then they go down, 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 but then dotted. And again, this is where it's tricky. Part here is connecting here, and then when I'm directly underneath, because dotted and then solid. And once I got that one, this one's a little bit easier. Dotted and then solid, and then the line of the intersection A, B, line AB. Okay, oh, and plane X and plane Y. Okay, now in the interest of saving a little bit of time, because this does take quite a while to draw, example E, three vertical planes intersecting at a single line, can be done right here, or it can be seen right here. Okay. So I'm not going to redraw that one, but I am going to redraw part F here. I should also say part C and part D can be drawn with a cube. Can oftentimes make things easier. So if I draw a cube, for part C here with the dotteds, horizontal plane Q could be the top or the bottom. Vertical plane N could be any one of the left, right, front, or back sides. Let's make it the right side here. N. And then we have a line that's connecting their intersection. Same thing with D. Can draw another cube. I'm doing this awfully quick. There's our cube. We have two vertical planes, X and Y. So let's go. Let's make X the front right and Y the back. And it's a little tricky because is that Y on the top or is it on the back? Is the X on the right or is it on the back? I'm telling you where they are. X and Y are both vertical planes intersecting at this line here, A, B. Okay. All right. F. Point P not on plane N. So let's start off by drawing plane N. And point P is not on it. 3 lines through P intersect plane N at points A, B, and C. So point A, point B, point C. We have a line through P hitting A, dotted, and solid coming out. Through P, through B, dotted, dotted, coming out underneath, through P, through C, dotted, and coming out. There's part F, part G. 2 horizontal planes intersect a vertical plane in lines L and N. So we have 2 horizontal planes. And again, I'm going to start off by drawing the top and the front of the vertical plane. And then this time I'm going to draw maybe a quarter of the back of the vertical plane. Then I'm going to start first with my 2 horizontals. Dotted because it's hidden, comes out. This first intersection here is line L. And then I'm going to draw another one. Dotted, solid, until I hit my second horizontal plane. And the intersection line. And this one is N. I just need to finish off back of my vertical. It's not perfect, but I think you can see the diagram there. All right. 3 planes intersecting at a point. Now, you can go with this one, but this is super hard to draw. The easiest one to draw is what we were doing a minute ago. Draw a cube. Just a quick sketch of the cube, and pick any of the vertices on that cube. This vertex is the intersection of the top plane, the right plane, and the front plane. And I have drawn part H, 3 planes intersecting at a point, right there. All right, as I promised, example 10 is going to connect to a few of those always, sometimes, never questions that we had earlier. So example 10 is an open-ended question. Suppose 2 points are in plane P. Explain why it makes sense that the line containing those points would be in the same plane. Well, if we have 2 points in this plane P, here's plane P, and I have 2 points in that plane. Now I got to connect those 2 points with a line. So what are some of the things that we know about planes and lines? Well, we know planes are flat. We know lines are straight. So if this line which hits the plane here and here, were to not be in that plane, it would somehow have to come out of the plane, curve, and then come back down into the plane to hit here. Again, coming out of the plane and then hitting here. Well, lines don't do that. They're not defined, but we know what they are. It's an undefined term, but we know what a line is. Same with a plane. It's an undefined term, but we know what it is. We know that planes are flat. We know lines are straight. Okay, since the line is not curved, then if 2 points of the line are in the plane, then the whole line must be in that plane. So the line would have to curve for it to come out of the plane, but lines don't do that because they're straight. Okay, part B. Suppose two lines intersect. Line AB, line BC, they intersect at point B here. How many planes do you think contain both lines? You may use your answer to part A to explain your answer. Now, I gave you this diagram on purpose to help you, to kind of give you a hint as to how to do this problem. There's a couple things going on here. One, points A and B are in the same plane, so line AB has to be in that plane. Points B and C are in a plane, line BC must be in that plane. Points A, B, and C are three non-collinear points. Three non-collinear points are the three-point postulate. Points A, B, and C must be coplanar. Okay, so again, points A, B, and C must be coplanar. They have to be contained in one plane. So if they're contained in one plane, then the lines that contain them have to be in that plane because of what we said in part A. So the line that contains points AB has to be in the same plane as the line that contains points BC, because A, B, and C are all in the same plane. So because these three non-collinear points are coplanar, these two intersecting lines must be coplanar. And that's the reason why two intersecting lines are always coplanar. Thank you.